Well, good afternoon. My name is Dr. Wes Hines. I'm the Nuclear Engineering Department Head here at the University of Tennessee. And welcome to our Wednesday Colloquium series. It's a little bit different today. I guess I don't know what different is anymore. We did this for a year and a half with COVID, and then we had speakers come back on campus. And now we've taken the opportunity to have the Zoom technology to allow us to have speakers come and speak without actually having to travel here. So today we have Dr. Shikha Prasad. She's an assistant professor in the nuclear engineering department at Texas A&M, and she leads the neutron-neutrino sensing laboratory. She received her PhD degree from the Department of Nuclear and Engineering and Radiological Sciences and a graduate student certificate in science technology and public policy from the Ford School of Public Policy, both at the University of Michigan, Ann Arbor in 2012. She also received an MSE degree in 2007 and a BSE degree in 2006 in nuclear engineering and radiological sciences from University of Michigan. She serves as the primary advisor of the Women in Nuclear section at TAMU at Texas A&M. She's an active member of the American Nuclear Society and the recipient of the 2017 ANS Young Member Excellence Award. That is quite an honor. You've joined a fabulous group of colleagues in winning that award. She has served as the academic advisor for the student chapters, the Institute of Nuclear Materials Management, which we have a chapter here too, and the Indian Nuclear Society at ITT Kanpur. Dr. Prasad served as the chair of the ANS Local Sections Committee from 16 to 17, and again in 19 to 21. So welcome, Dr. Prasad.
Great. Well, thank you so much for that introduction. I appreciate that. And I'm excited to be talking to you all because I used to live on that campus when I used to work at the Oak Ridge National Lab. So it's always nice to be speaking to the University of Tennessee, Knoxville nuclear engineering students. Now, my talk today is going to be on next generation portable antineutrino detectors using semiconductors. So while I'm presenting this work, there's a lot of effort that has gone into this. The major contributors of this work are my PhD student, Wang Ang, and the inventor of the detector technology, or the lead on the invention, that's Dr. Rupak Mahapatra in the physics department, all of them at Texas A&M University. So to give you, and let's see if I can go, there you go. And to give you an outline of the presentation. So I will first speak about how antineutrinos are produced in a reactor, then potential applications in nuclear engineering, okay, for antineutrino detection. What are the existing methods? What's the technique for detecting antineutrino? Following that, I will speak about coherent-elastic-ν-nucleus-scatter, and that's the new mechanism that we will be investigating in this talk. How is it better than the previous or the existing, rather, I wouldn't say previous quite yet, the existing state of the art. And how does it work with semiconductors and transition edge sensors? Following that, I'll give you the antineutrino spectrum calculation for the reactor at Texas A&M, for which this analysis was performed, and I'll talk about the cross-section, and then how the convolution of the two gives you the reaction rates and insight into how we can perform better with this new technology. Finally, I'll end up with the current measurement setup at the reactor and the future plans. So if you're looking at the screen, you'll see a few images. The one on top left is the detector technology that's fabricated here at Texas A&M. It originated from Super CDMS and CDMS and Super CDMS at Stanford, starting at Stanford, where they were interested in dark matter search. So that's how it started. These detectors are cooled down. They're much smaller, about the size of a dinner plate, if you will, so much smaller, much thicker, but they have to be cooled to millikelvins. So those are the detectors shown over here. On the right, you've got the Texas A&M 1 megawatt trigger reactor. Okay, so that's how we're hoping to detect these antineutrinos, and that's where the existing setup for the measurement is. But at the bottom, I've listed a few other applications other than just reactor physics applications, where we could be even looking at antineutrinos coming from the Earth in geophysics applications. On the right, looking at neutrinos from solar storms, okay? And these both have engineering applications. Geophysics, obviously, and knowing geodynamics is important for earthquake prediction, for volcanic eruptions, and the right is important because solar flares can really take down electrical grids and so on and so forth. So let's take a look at, we will concentrate on reactor physics applications here and reactor monitoring. So antineutrinos are produced in the beta decay process. Here you have a neutron, which will decay into a proton and an electron, along with an antineutrino. Okay, and this kind of reaction is most seen in neutron-rich fission products. Okay, and here, when a fission happens and fission products are released, the antineutrinos can amount to about 5% of the energy released. So if you are able to see this little table at the bottom, this is specific to the Nuclear Science Center reactor, the TRIGA reactor here. You see that a uranium-235 fission up top will emit a total of 200 MeV of energy. And then in the third column, it shows that the antineutrinos together will carry 9 MeV of the energy, whereas the total number of antineutrinos carrying this 9 MeV is 6 or 6.14. So on an average, we are expecting about 1.5 MeV per antineutrino. Okay, uranium-238 also will, when it fissions, it'll emit about 11 MeV in its total antineutrino energy, carried by 7 antineutrino. Now let's compare that to Pu-239, where the energy carried by the antineutrinos is 7 MeV, and that's carried by 5.5 antineutrinos on average. So if I look at the amount of energy one antineutrino carries, that drops down from 1.5 for uranium-235 to plutonium-239 to 1.3 in plutonium-239. So there's a bit of a difference, and that gets our hopes high that if we're looking at the first moment of the distribution, if we're looking at the mean, we might be able to tell some information about uranium. Is it uranium-235 or is it plutonium-239? And if you all know, since you all are experts at reactor physics, you realize that for large reactors, for commercial reactors, when we begin operation, you load in fresh fuel, but as time passes, plutonium builds up, right? So the number of reactions shifts from uranium to plutonium-239, so much so that by the end of cycle, we're looking to 40 to 50% of the fission reactions happening due to plutonium-239 in large commercial reactors. So in that case, this could be a signature of telling where in the fuel cycle we are, right? And what's the age of the cycle, if you will. And at the very end, I've shown a uranium-238 transmuting to plutonium-239 by the capture of a single neutron. So this last reaction is different from the previous four. Previous four is the energy released in fission, whereas the last one is the energy released in a capture reaction. And if you note the amount of energy carried here, it's 1.2 MeV carried by 2 neutrinos. So that's 600 keV neutrino energy per neutrino, quite a bit lower than the fission antineutrino. So that's also something we'll try to investigate later on. Okay, so with that in the background, let's take a look. So hopefully I have motivated you enough to realize that reactor monitoring might be possible with sensing antineutrinos from the reactors. You could tell the total power, the isotopics, right, and the burnup of the fuel. And by doing so, you could provide a way to calibrate X-core detectors. You could detect presence of covert reactors or use nuclear fuel storage. You can measure the uranium to plutonium ratio, measure the age of the fuel, especially, and that would be especially interesting in used nuclear fuel. Determine reactor burning and breeding ratios. Okay, so that is breeding would be a U-238 capture that I just spoke of. And in advanced fuels, such as molten salt reactors, where tag and track may not work as well, or where something is completely sealed and underground, this might be another way of measuring the power. Further, post-accident monitoring is also something that people have tried to do or are trying to do or investigate with antineutrino detectors. So talking about breeding and fissions, if you take a look at the top right, you have here 1/8 of a core from a prototype fast breeder reactor being constructed in India. And what you see is in the center, you've got the main core, which is fission, and outside you've got a region of blanket where you would transmute and create fissionable material. Okay, so this, in such a configuration, you want to keep a track of how much fuel is being bred in the reactor core. So this plot here by Cogswell and Huber shows that in terms of breeding, okay, the breeding lines here are shown in these, that's the dashed line. So, okay, so that's the capture. Actually, I'm sorry. The red is your capture, the red solid is your capture, and the blue solid is your capture. So that can be seen in the middle. And then the fission lines are the dashed lines. So if you are looking at a difference between the fissions in the core and in the blanket region, you can clearly tell the difference here, okay, as to where the antineutrinos are coming from by looking at the magnitude, the spectrum, okay, of the antineutrino flux as a function of the energy. So we decided to take a look at this a little bit closer for uranium-238, since there seems to be quite a bit of difference between uranium-238 fission and capture in terms of the when looking at the antineutrino spectrum. So at the bottom, you have the uranium-238 antineutrino spectrum. The blue line is just showing you uranium-238 fission. Then the red line here, where you pretty much, if you look over here on the right, you can see the red line only below 1.5 MeV. That is showing fission plus the capture. Okay, so then in this case, we are able to distinguish the antineutrino spectrum where you're breeding new fuel as opposed to just fissioning. Okay, but the condition is that you need to be looking below 1.5 MeV. So that's something that we can note looking at the bottom right graph. All right, so let's now take a look and see what are our present methods of detection. So the current method and the traditional method that people use for detecting antineutrino is basically the antineutrino interacting with the proton, making a positron and a neutron. So this is the current method. The cross section for this reaction is really small. Here it says 10 to the negative 18 barns, so it's in picobarns. And that, if you think about the cross sections, if you have a cross section that is that small, obviously you will need to have a detector which is really, really large. Sometimes they can even be as large, so they can be tons to kilotons. On the right hand side, there is a state-of-the-art IBD detector, inverse-beta-decay detector, and you can see that there is a boat taken over here to sort of go across the detector. So it's a huge detector, almost a stadium-sized detector. So that's one of the limitations of IBD, that they tend to be pretty large. Then the other feature of IBD is that it has a threshold of 1.8 MeV. So anything that's under 1.8 MeV, for example, that breeding reaction that we were looking at on the previous slide, will be missed. Okay, that difference we won't be able to capture. And the third thing is it really results in a loss when you can't see below that 1.8 MeV, because if you look at the previous, if I may go back to the previous slide, if you look at it, the flux spectrum really decreases very fast logarithmically, and the y-axis is logarithmic, okay, as energy increases. So you are missing out on a lot of antineutrinos with a threshold that high. Okay. So what we need is an efficient detector which can provide high signal to noise quickly. It can provide detailed spectrum information, which we can use for isotopic analysis and understanding what's kind of reactor physics operations is going on inside a reactor, breeding or not breeding, and which is low cost, it's low maintenance, and it's portable. Okay, so one alternative that people have been recently very excited about is the coherent-elastic-ν-nucleus-scatter. On the right-hand side is a plot which shows the intrinsic cross-section for interaction for the coherent neutrino nucleus scatter, that's we'll abbreviate it as CENNS, which is shown in red, and then the inverse beta decay, which is a traditional method, shown in green. So just by looking at this plot, it may seem to you that, wait, this is a really good method, and it looks like the cross sections are, you know, about 1,000 times larger, if not more. So it seems very promising. So we'll try to see if it is as promising as it sounds, and if there is promise, what are the challenges? Okay, so we'll look at coherent neutrino nucleus scatter mechanism as compared to IBD. So the way the coherent neutrino nucleus scatter works is that you have an incoming neutrino, which basically scatters against the nucleus, and there is a recoil. Okay, this was first measured very recently in 2017, though it was proposed first in 1974 by Friedman. The equation that we will use to solve for the cross section for coherent neutrino nucleus scatter is shown over here. Okay, and I have a small video over here to kind of demonstrate. I think it's pretty obvious, but if you look at this, there is a, if you can think about how the rebound is happening, it's pretty simple. The neutrino is a very small particle, okay, and all it does, it comes and it strikes against the large nucleus, and there is a rebound. Keep in mind, the nucleus is so much larger than the small nucleus, neutrino, right? So the mass of a neutrino is not even, is a couple of eV per c square, whereas the mass of a nucleus can be much, much larger than that, on the order of GeV per c squared, right? So, or even greater. So we're looking at orders of magnitude difference here, and the rebound is very small. So the signature, which is the energy that's deposited in the rebound, is going to be very, very small. All right. Okay, so with that, I am summarizing on this slide current experiments that are using CENNS. So coherent at Oak Ridge National Lab, which is using the spallatial neutron source, okay, is one experiment that's using this particular reaction. They were the first to observe it in 2017, and definitely that was a Herculean task that they've done for the physics community and engineering community, so that was great. The nuclear threshold they have reported has been 20 keV to 13 keV. They use scintillation-based detectors for this particular reaction. Now, if we contrast it to the minor experiment, which I've been talking about at Texas A&M, it's a 1 megawatt trigger reactor, which is using germanium, silicon, and sapphire detectors, and they're hoping to get the thresholds down to 10 eV. So that's very, very small, because the nuclear recoil is really very small, on the orders of eV. Then there's other experiments here, Texono in Taiwan, Connie in Brazil, Nucleus in France, and Red 100 in Russia. Okay, the thing to note here is that there are two types of technology being used: scintillation and semiconductor-based technologies. The scintillation technology is a little bit more mature than the semiconductor-based, but both of these technologies have not measured antineutrinos from a reactor yet. So it's a pretty interesting race right now, race to be the first. So what is a technology that's been deployed at Texas A&M with the minor experiment? So if you look at this germanium detector right here, you basically have an antineutrino scattering with a nucleus going to its own place. The temperature that the germanium detectors, or the stack of germanium detectors or silicon detectors, kept at is less than 10 millikelvins. Okay, so now if you look at this bottom right figure, what happens is when the germanium or silicon nuclei rebound or recoil, there is a certain amount of energy that's imparted that is carried by the phonons. The phonons then in turn go to the aluminum, okay, and that breaks Cooper pairs. The Cooper pairs then will go to tungsten, okay, where even a small change in temperature will cause for a current to flow. So that's the cartoon shown on the right, where you see a small change in temperature is causing a current to flow. And that's the basic mechanism and the unique aspect of these semiconductor detectors using the transition edge sensors, or calculating that minute change in temperature. Okay, so with that technology being shown, let's talk about the reactor here. So the Texas A&M Nuclear Science Center reactor is a 1 megawatt trigger reactor with 19.75% enrichment. The fission rate in that reactor is 3.1 times 10 to the 16 per second. The antineutrino production rate is 1.97 times 10 to the 17 per second. And at 10 meters, where we are trying to calculate the reaction rates, we're looking at a flux of antineutrinos at 1.5 times 10 to the 10 per centimeter square per second. The yield is 6 per fission. So how are we going to go about it? Well, the method is pretty simple. You determine the antineutrino flux for the trigger reactor, right, based on the fissions. Then you calculate the sevens cross section for the detector of your choice. Okay, so we'll show it for silicon and germanium. We then convolve the antineutrino flux. We multiply them together with the cross sections that we have calculated in step 2. And just to let you know, we are only calculating the reaction rates, not the ionization and phonon production response in this case. Okay. So for calculating the antineutrino spectrum model, we have 2 methods that we could pick from. The first one, which is the one we chose, is the ab initio summation method. Here, you basically extract all the information from the data libraries about the fission products. Okay, and there's hundreds of fission product for each fissile isotope that's fissioning, where it's U-235, Pu-239, U-238, or Pu-241. Each of them will have several hundreds, and actually they have several thousands. The one we are tracking are only those which have a yield greater than 10 to the negative 6. So with that, and for each of those fission products and isotopes, there may exist several isomeric states, okay, in the beta decay. So we have to then go back and calculate all of that. Sometimes the data libraries may not be enough. So we have calorimetric measurements that we use called the tags data. And sometimes we just use theoretical, but these are only a few, if like 100 or so amongst the 8,000 branches that we are following. So for most of this, the data library, the end of 8 and Jeff together are actually pretty good. The second method is using an electron spectrum conversion method. So here we realize that in an antineutrino emission, there is also a beta particle that is emitted, right? So here, what people have done in the past is that they have done experiments on the beta spectrum and calculated the beta spectrum and the measurements for each uranium-235 fission products, U-238, Pu-239, and Pu-241. Now, knowing the beta spectrum, you can then calculate the antineutrino spectrum, because your Q value is really going to be carried between these 2 particles, right? The beta and the antineutrino for the most part. So these are the 2 methods. The reason, and the electron spectrum conversion method, where you go from the beta spectrum to the antineutrino spectrum, is considered to be more precise because it's been measured, verified, validated. But it's only limited to 2 to 8 MeV. And as I had shown you a few slides ago, we're interested even in lower energies. That's where a lot of information lies for reactor physicists and reactor engineers. So we will be also, so that's another reason why we'll be using the ab initio or the summation method. Okay, so here I'm showing you the calculation of the antineutrino spectrum. So rho here is going to give you the number of antineutrinos released per energy, and that's shown on the y-axis in the plot. So the way you do it is you first have to track for each fissile isotope. So for U235, U238, Pu239, Pu241, you need to track all the fission products, like I had mentioned, and then you need to also know for every fission product what are the major isomeric states that will be for the beta decay that will be contributing to the antineutrino spectrum. So, so once you sum them up, you come up with the final antineutrino spectrum that is shown on the right. As you can see here, most of the fission in this case, okay, now keep in mind, this is for the Nuclear Science Center research reactor. In this case, there's been very little burnup. So most of the fissions are still occurring to uranium-235. So if you look at the total, which is the green, that pretty much overlaps on, with the pink, which is a uranium-235. And if you look at the plutonium-239 fraction, since there's very little plutonium-239 in the reactor right now, it's only 2%. The U238 fission fraction is about 1%, and Pu241 is very small, not even 0.1%. Okay, so that's your antineutrino spectrum. We'd like to see how, because there was so much bookkeeping and adding, across several thousand states, we wanted to see how it matched up with others who have done similar calculations. So here we picked up some of the most cited antineutrino spectra for each, the conversion and the summation method that we discussed a couple of slides ago. So our work is the one in cyan, that's the blue, or the light blue, okay? And the dashed line in black is by Hayes from Los Alamos National Lab, and they use the summation method. The red marks are from Huber et al., and they had used the conversion method. So these comparisons are shown here on the left for uranium-235 and on the right for plutonium-239. So looking at this, although I'll tell you it is a logarithmic scale, it looks like the agreement is really good. But because it's a logarithmic scale, I would like to point out that at higher energies between 7 and 8 MeV, our disagreements are about 10%. So we're trying to look into that and see if we can reduce that further. But so far, I think for the sake of calculating detector response, we're pretty satisfied with this result that we have. Then moving forward. So moving forward, we calculate the cross section. So on the top right here, you have the cross section shown as a function of energy. As you may see that the cross section is given, actually I chose to give here in centimeters squared just to let you appreciate how small these cross sections can be. So we calculated the cross section for natural germanium in blue, natural silicon in red, and IBD in yellow. So as you can see, each of these is like an order of magnitude apart. If I compare germanium to IBD, it looks like the cross sections are 2 orders of magnitude. Actually, this is more like 4 orders of magnitude larger, and so 3 to 4. And silicon, it's 1 order of magnitude. I think I misspoke. The germanium is about 2, looks like it's 2 orders of magnitude, and silicon is about 1 order of magnitude. But this is not the final, this is just a cross section. So we need to convolve it with the antineutrino spectrum. So what we did is we calculated the flux weighted average cross section. For germanium, it's 4 times 10 to the negative 4 picobarns. For silicon, it's 3 times 10 to the negative 5 picobarns. For IBD, it's 1.8 times 10 to the negative 6 picobarns. So that this gives you, for the reactor flux of antineutrinos, what my average expected cross section is from a 7's reaction. Okay, and this was calculated with a physical nuclear recoil implemented in the calculation. And so we said that anything under 20 eV, we will not be measuring. So we're only interested in recoils which are at least 20 eV or greater. And that was motivated by what has been achieved here in terms of looking at the response of the minor detectors. Okay, so now this is the real reaction rate so it's kind of interesting. So looking at the cross section can be a bit deceiving, right? Because it looks like they're a lot more, orders of magnitude larger than IBD, a lot more promising. But think about it, we're going to be convolving it with the antineutrino spectrum, which tends to be much more skewed to the left, okay? So the fact, let's go back here if I can. So the antineutrino spectrum peaks at lower energy, whereas the 7s cross section will decrease as a function of energy. Okay, so there is a mismatch there, and that's what is shown when we convolve those two. And sure enough, you see that the detection rates are better, still better with 7s, but not as much of an advantage. The natural germanium is showing about 20 times more events per day. So that shows, and that's shown over here in blue. It's showing events per day, which is 43.37. Natural silicon shows 7 events per day. And if we compare it to the IBD, it's showing 1.78 events per day. So now we can talk about, what was our advantage in terms of detection rates or reaction rates, okay? So now we see that germanium does in fact give us a 20 times greater increase in the detection rates. The silicon is giving us about 3 to 4 times greater number of events in terms of reaction rates. Now let's look at how low can we go in the energy. So at the bottom over here, you've got the material that was used in the first column, germanium, silicon, or IBD, or in fact the reaction that was used. And the second column gives you how many antineutrinos did we fail to detect, what percentage of the reactor antineutrinos did we fail to detect. And the third column in the bottom table shows you what was the threshold of detection in terms of antineutrino incident energy, if we're assuming that the smallest possible detection we can make with these transition edge sensors is about 20 eV. Okay, so for germanium, it looks like we missed 32% or 33%, 32.89%, 33% of the antineutrinos, and the threshold was 820 keV, okay, 0.82 MeV. With silicon, we lost only 20% of the antineutrinos, and here our threshold was 0.51 MeV. With IBD, though, we lost 66% of the antineutrinos. That's 2/3 of the antineutrinos, okay? Because if you recall, the threshold for the IBD, if you're looking at this black curve on the plot, is 1.8 MeV. So just look at, and I guess I did put this one on a linear scale instead of a logarithmic scale to let you appreciate the advantage that we could have with this technology once it's made mature. Okay. And these are pulse height distributions. We've calculated the pulse height distribution. So here we're trying to give you the number of counts in per day per EV of nuclear recoil of the detector of interest. And on the x-axis, we have the recoil energy of the target material. So this was just a calculation detail. This was done deterministically because we know the differential cross-section for interaction of the 7s reaction as a function of the incident antineutrino energy and the recoil of the nucleus. You can integrate that and basically divide it by the differential to get the probability that given an antineutrino came in at a certain energy, what was the likelihood that it would produce a threshold TR of our choice. Okay, once you convolve this probability with the reaction rate, I don't know if you're able to see it at the bottom over here, then you can get the total counts. Okay, all right, so that will help us, and especially in terms of pulse heights, because at the end of the day, it's very promising to see that we're getting more reactions, But the problem is, so even though we're getting a lot more reactions, the problem here, the challenge here is those reactions produce a very small, deposit a very small amount of energy. So the real challenge is to capture that small energy deposition, and that's where these detectors are doing a good job. Okay, so now let's take a look at how important these thresholds of detection are. So I spoke about nuclear recoil. So if I'm comparing within CENNS reaction, these two different materials, okay, germanium and silicon. In the second column, I have 20 eV of nuclear recoil. And then in the third column, I have 100 EV of nuclear recoil, just to see what kind of impact it makes. You see that 20 EV nuclear recoil will give you 43 events per day, and 100 EV nuclear recoil in germanium will give you 37 events per day. So it looks like for germanium, it matters a little bit. For silicon, however, going that low and putting in that effort to go from 100 EV to 20 EV may not be as satisfying, because you're really gaining a little bit. You with the 20 EV, you can get 7.8 events per day, whereas with the 100 EV recoil, you see about 7.5 events per day. So there's a difference of about 0.3 events per day. The difference is much more significant in the case of germanium. And that's what you see on the right-hand side. We have shown two curves, one for natural germanium and one for silicon, where we have shown you the detector response, the cumulative detector response in events per day as a function of the recoil of energy. So it looks like, you know, you do gain in the events per day as you go lower in threshold, but only up to a certain limit, right? And after 100 EV, it's a law of diminishing returns that, you know, for this case. So, but just to kind of give you some context as to how low we've been able to actually achieve and demonstrate and show at the reactor here, it's about 45 EV with the sapphire detectors. So that's where minor is right now. I would like to go even lower. Okay, so the minimum detectable antineutrino energy here. So what if with the 20 EV nuclear recoil threshold in germanium, we're looking at 800 keV of MeV. When we go up to 100 EV of nuclear recoil, it's 1.84 MeV. So 100 EV nuclear recoil will not be advantageous if you're looking at thresholds. Like if you're making the argument that, you know, we have a chance here looking below the IBD threshold. Well, if that's true, then for the germanium detectors, you ought to be below 100 EV of nuclear recoil. For silicon, there is still an advantage in looking below the IBD threshold. At 20 EV, you're looking at 0.5 MeV of minimum detectable antineutrino energy. For silicon, even for 100 EV of nuclear recoil threshold, you're looking at 1.14 MeV of minimum detectable antineutrino energy, which is still below, well below the IBD threshold of 1.806 MeV. Okay, so with that comparison being done, let's take a look at what we have planned. So currently we have a reactor here, as you can see at the NSC. It's a trigger reactor that's contained in a swimming pool side of a large pool, and it's about 3 meters from the core. The advantage of the reactor here is that the detector, so where it says at the lower right, lower research level, that is where the detection setup currently is. You can see the fuel assembly right in the middle. Now, the advantage or something interesting, an interesting feature of our setup is that in the years to come, once we have demonstrated that we can measure reactor antineutrinos with our detectors here, in the years to come, we plan to use this setup to move the reactor assembly, okay, horizontally. So if you are looking at this assembly, it is actually on rails, so it can go far, and we can change that distance from 2 meters to 10 meters. So we have that capability with the trigger reactor of changing the reactor to detector baseline distance. And that's being planned for some interesting measurements by the nuclear physicists as well. And currently the payload in these few millikelvin fridges are about 4 kg, but we can go as high as 30 kg, so the detector payload can be increased. Okay. These are just, I was given 45 minutes to talk, so I'm just going to wrap up here. We've been working a lot on reactor on and off experiments, and I mean, the first thing to do is to show that we can even measure before we start doing the antineutrino spectrum measurements. That'll be the next step. So we've been working a lot. The real challenge here has been the background. Okay, so definitely we get different signatures on reactor on and off, but the problem is that when the reactor is on, you get a lot of signatures and interactions in the detector due to the neutrons and gamma rays. Further, there are secondary reactions that are causing the shielding, and there may be even reactions happening within the detectors that could be contributing. But for the reactor spectrum, where the energies are much smaller, the likelihood is much smaller for the third category. So we've been trying various detector designs with veto, without veto, where you can tell whether or not there was an external background event. So trying to limit the neutron and gamma signature so we can obtain the antineutrino signature. All right. So this work, we have shown that semiconductor detectors they have the potential to be the next generation of detectors for detecting neutrons, antineutrinos, and they have, I think we've done good work in showing that we can achieve low thresholds for doing that. In this particular talk, I showed you that the CENNS reaction has better intrinsic efficiency. And when you convolve it with the antineutrino flux spectrum, the germanium detector can provide 20 times greater reaction rates, and silicon can provide about 4 times greater reaction rates. Okay, unfortunately, the real problem for us is not going and pushing the threshold as much, but the problem has become the background that we see. So on the right over here is the student who's been working on with these detectors. Up top, where you see a circle, that's the fridge in which these detectors go to cool them down to a few millikelvins. And at the down right, you basically have the fridge being surrounded by all that lead. And there's behind the lead, there's also a whole bunch of water shields, actually, where the black screen is. And that is where the reactor fuel assembly is contained. That's the core. So it's about 3 meters from the center of the fuel assembly all the way to the detectors. In the future, we're now working on getting this analysis. We're translating this analysis for AP1000, where you do see a lot of change in uranium and plutonium profiles to see what kind of reaction rates we can predict. And finally, incorporating the pulsar distribution, we'd like to go back to and reconstruct from the detector response the original antineutrino spectrum. So that ends my presentation today, and I'm happy to take any questions at this point. Thank you.
So really great presentation. What type of a response do you get when the reactor is turned off? And you're saying that it looks like most of this background is from the reactor, the gammas, the neutrons, rather than cosmic or something else. Does basically the whole response go away when you turn the reactor off, or do you still see quite a background from other things?
Yeah, great question. I like that. And I kind of went quickly. So if you look at this.
Oh, there it is. Okay.
Right. So the red here is the reactor on signature, and the black here is the reactor off signature. So we've been working on some chi-square numbers to see what kind of confidence we may have in the difference in the two. But I think the main problem right now is to tell how much of that difference, so there certainly is a difference, but how much is that difference due to not having fissions and the neutrons and the gammas that are being emitted from the fission, as opposed to the antineutrinos that were being emitted from the fission. So we're using pulse shape analysis, a lot of signal processing, a lot of machine learning is going into that. And yes, so there is a different team working on that aspect.
So it looks like a lot of your background is background, you have all this, I guess, background due to the neutrons and gamma rays,
That's right.
but it's not necessarily the ones produced by the reactor.
Yeah, so mostly they're the ones produced by the reactor. That's what
But when the reactor is off,
right.
where
That's right.
where are all the counts coming from?
Right. Okay, now I see what you're saying. So yes, so in that case, those would not be from the reactors on and off. But if we take I guess the area under the curve, as I understand, we are getting a significant when the reactor is on, a significant amount when the reactor is on. When it's off, that's a good question. I don't think we really have an answer to that yet, where it's coming from. I mean, obviously, some of the things that others have looked at, we haven't been able to isolate, like, for instance, muon production will create some antineutrino signatures as well. But for that, we will need some sort of position sensing to kind of tell the direction of the antineutrino. And that is yet to be done. So we can't really say for sure. Yeah.
So I see that Dr. Hogue from Oak Ridge National Laboratory has a question. She's basically saying, when the reactor is off, how long did you let it stay off for all the, fission products to decay away? Because it's all those decays are still causing the antineutrinos.
That's
so
right. That's right.
you probably need to leave this off for a sizable period of time to let all those decay away.
Yeah. So sometimes, well, that I can answer, and that downtime can range from, it's typically on the order of days and sometimes longer. So that's the kind of decay decay time that we're looking at.
So just kind of looking at the figure to the right there,
right,
where it has an energy spectrum with counts, with the reactor on and reactor off. It looks like you're almost getting as many counts with the reactor off than on.
That is right.
Some energies like down at 5 keV.
Yes, 5 keV
7.
to 30 keV counts. Yep. And those energies right there are shown as a function of right. So these should be shown now as a function of recoil to the right. But we're able to go much lower than that. And I think the calibration for this one might be a little bit different. I don't know exactly which detector was shown for this one on the right-hand side. But yes, again, I think I would agree with you that the reactor on and off curves are pretty close there.
Okay, other questions?
I think there's another one.
Oh, Jason's putting one in.
So I can ask it. So as you know, the first observation of SEVNS was at the CENNS here in Oak Ridge with the cesium iodide. And so now you're doing semiconductor detectors, and it's really cool, by the way. I really love what you're doing. So thanks for giving us the talk. I was wondering, because I don't think I saw a comparison. Do you know how the SEVNS cross sections of the germanium and silicon that you showed compared to those of the cesium and the iodine? And then I was also wondering about the background subtraction. I know they did it. They did a background subtraction to kind of understand that you could observe it. Is yours going to be similar or different, or? Right.
So that's what we're working on right now. The background is a function of energy. It just kind of, it has a little bit of an exponential shape to it. Is it similar or different? I've looked at background for these various SEVNS reactions that I spoke of, not necessarily for the scintillation one that you're talking, not the coherent, but we've been looking at the coni and the nucleus. So they actually look pretty similar. The shapes at least look very similar in terms of background. And the background is where really a lot of work needs to be done at this point. The detector development has taken place, but we're really not able to understand the background as much.
Okay, thanks. And what about cross sections? Are they better for germanium and silicon than for the cesium and the iodine? Or?
Right. So that's interesting. You asked that question because that's something we are planning on working on next, Jason. So hopefully I'll have an answer for you in the next few months. Because I think it's only fair to compare the other, we're basically comparing against IBD, but we need to be looking at scintillation detectors because they're quite a mature technology right now.
Okay. Sounds good. anyways, yeah, I love the germanium. We've got plenty of it too. So if you need more, you can talk to me.
That would be fantastic. That's pretty expensive. Great. Thank you, Jason. Yeah.
Other questions?
Dr. Hines, I'll ask another one if no one else has any.
Yes,
this
certainly.
is Karen again. I'll turn on my video so I can see you. I think this is really interesting as well. So thanks, Dr. Prasad. I have a question about advanced reactor kind of use of this as a monitoring mechanism or safeguards, purposes or whatever. So can you talk a little bit about kind of the practicality of it, like the size of the detector that would need to be there and where it could physically sit? I know you guys are just in the early stages of this, but can you talk any about that, about how you might see this included in kind of a safeguards approach in the future?
Sure. I think in terms of a safeguards approach, we're hoping that we would still be close enough to the reactor core itself. And so we're still looking at scenarios where we are in the compound of or in the periphery of the reactor building. And in terms of, so not looking at 100 miles away, because there are a lot of long baseline experiments and setups being planned. So we're looking more at short distance measurements. Okay, so close baselines. And in terms of the benefit then, so what we are hoping is if there was a movement of some sort of a significant quantity, so let's say plutonium, right? One or two significant quantities of plutonium were moved, would we be able to tell that difference? And again, that sort of difference goes back to our calculation of detection rates, and actually even further, when we looked at the average amount of energy carried by an antineutrino. So we're interested in looking if we could look at spectroscopy and tell that difference, whether there was a movement of uranium and maybe plutonium and things like that. So so those are the two things that I can think of in terms of answering your question. But there's other opportunities that will need to be investigated, which people have tried a little bit with IBD, which would be more promising, and that is looking at spent nuclear fuel. So if you look at the fission products from spent nuclear fuel, you'll see that as the age of the spent nuclear fuel, once it's outside the reactor, as the spent nuclear fuel age increases, the cooling time increases, the antineutrino spectrum starts to shift more and more to the left. So, and it falls below the IBD. So it would be interesting to see if that kind of a shift could be measured with these current detectors that are being proposed. So that would be another one, but that will have very small event rates. So to get a meaningful information in a possible mission time would be a question mark, right? So when we talk about mission time, we're looking at 90 days of mission time. So to get that sort of information within 90 days will be a bit of a problem.
Thanks so much. And just to clarify on that, so would that be like there would be a 90-day measurement kind of time, or would it be like continuous monitoring of just basically like it's there, it's part of the, it's a stationary detector and it's just kind of always running and you're just pulling data?
Yes, so
analyze?
That's right. So your detection time, so it's unusual, right? So when we do detection and measurements in our in normal laboratory, we look at measurement times that are minutes or hours, but here we are looking at a cumulative 90-day detection time where you let these detectors run for that long. Because if you look at the event rates, they're very, very small, right? With a couple of events or a few events per day that we're looking at, to accumulate enough events to answer with enough confidence where there was movement or not of the fuel, you do need to have much longer detection times. And to put it in the context of IAEA, it requires that timely detection be done within 90 days. You'd want to be restricted to those 90 days.
Thanks so much.
Yep.
Yeah.
You're welcome.
Great question, Karen. Karen happens to be a TAMU grad too.
Oh, that's fantastic.
I'll let that one out of the bag.
Gig 'em.
Great.
Uh-oh, gig 'em.
Yep.
Okay, do we have any other quick questions? We're just about out of time. Okay, if not, I'd really like to thank Dr. Prasad and exciting research you're doing down there in Texas, and best of luck to your future. Take care.
Thank you so much. Appreciate the opportunity. Thanks a lot. Take care.
Thank you.
Bye-bye.